So, we have till now known what is a p-type semiconductor and an n-type semiconductor. Now, what will happen when you combine p-type semiconductor and n-type semiconductor? That means you sandwich them or make a junction between p-type and n-type. That we will be discussing today. When you have p and n type of semiconductors combined together by some appropriate scheme like ion implantation or diffusion, which is this process is not mechanical, mind it, to not to disturb the crystalline structure of the silicon or germanium semiconductor, which is the base material. Properly formed p-n junction will be having p-type on one side and n-type on the other side. So, if we consider now this p-type and n-type semiconductor making a junction in between them, then here we can notice that the p-type semiconductor has the acceptor ions as well as the carriers which are holes, positively charged carriers, and n-type semiconductor has donor ions and electrons. So, now we have majority carriers holes in the p-type and the electrons are majority carriers in n-type along with the ions, acceptor ions on the p side and the donor ions in the n side, which are negatively and positively charged respectively. Now, there will be a difference in concentration or there will be a concentration gradient of holes from p to n side, as well as there will be a concentration gradient of electrons from n to p side. So, whenever there is a concentration gradient, then the carriers holes and electrons will try to flow from a higher concentration region to a lower concentration region, just like whenever there is a pressure difference in the water level between two places, then higher pressure water will flow down to the place where pressure of water is low. Exactly similarly, because of this difference in concentration, the holes will start moving from p type to n type, and this process is called diffusion. So, here these holes will be crossing over the junction from left side to the right side, and the electrons will be crossing the junction from the right side to the left side. This process is called diffusion. So, diffusion of holes and diffusion of electrons will take place whenever you bring p-n junction together. Now, as these carriers holes from left side cross over to the right side and electrons cross over from right side to left side, what will happen is that there will be recombination of charges, because holes will be recombined with free electrons and electrons will be recombining with free holes. Then, because of the recombination of these charges, now what will happen is that the ions, that means the acceptor ions on the p side and the donor ions in the n side, they will be now surfaced out. Surfaced out means they are now uncovered, because earlier in this case you have seen that every acceptor ion has a hole which is positively charged along with it, that charge neutrality was maintained. Similarly, in the n side, donor ion had a free electron attached to it, that means there was also charge neutrality conserved. But now, as there, because of the recombination of holes and electrons, these charges of the ions now become uncovered. That means, along with it there are no carriers. So, they are now uncovered negative side on the p side and uncovered negative charge on the p side, and the uncovered positive charge on the n side will be there. Now, that is why these bound charges will be forming layers of negative charge on the p side and positive charge layer on the n side. So, this region where there will be no mobile charges, only bound or fixed charges are there, this region is called the depletion region, or it is also called space charge region. So, this region is devoid of the free carriers. So, under open circuit condition, that means we are not connecting this p n junction to any circuit, it is open circuited. So, we will be now having in the depletion region only immobile charges. So, these immobile charges are forming two layers, negative charge layers on the layer on the left side, that means p side, and positive charge layer on the right side. So, that means it is like a potential is developed, and the potential is like positive on the right side here and negative on the left side. So, this potential will be now preventing, or it will be stopping further movement of free charge carriers, because as this side is positive and this side is negative, these holes are now repelled by this positive charge on the right side. That means, these holes cannot now cross over the junction and come to the n side, because this will be stopped or prevented by this positive potential which is developed. This is also called barrier potential, because of this fact that it is now giving a barrier to further movement. So, these holes now cannot move to the right, as well as the electrons now cannot move from n side to p side, because this bound negative charge layer on the left side or the p side will be preventing it from crossing over to the n side. So, now this potential is now creating a field, that field is say E. So, this field will be produced, and this potential barrier will be now preventing any further movement of holes and electrons. But if you remember that there are also thermally generated minority carriers, which are the electrons on the p side and holes on the n side. These are thermally generated. So, now this E, which E is developed because of this crossing over of holes and electrons, and because of this barrier potential being developed, this field, the direction of the field is such that positive on this side and negative on this side. So, now these minority carriers will be attracted with these electrons, which are minority carriers for the p type, will be attracted by this field, because it is a positive towards right, and the minority carriers which are holes will be attracted by this negative of the potential. So, that means, now because of this field being produced, there will be drift of these minority carriers, and due to the drift of these minority carriers, now a current will be flowing. The direction of this current is just opposite to the direction of the diffusion current, because of diffusion the current was from left to right, and because of drift the current is from right to left. So, open circuit at p n junction will be having no current, that is total current will be 0, because to reach stability it will be under steady state or stable condition, the diffusion current is equal to the drift current. So, finally, the total current in this open circuit at p n junction will be 0. So, we have seen that the diffusion current is due to the concentration gradient, and diffusion of holes take place from p type to n side, and diffusion of electrons from n side to p side, and holes and electrons recombine because of this diffusion, and they uncover the bound charges. So, a layer of positive fixed charges is formed on the n side of the region, giving rise to a potential, and that potential is known as built-in potential, or sometimes you will be also finding that it is named as barrier potential. So, this uncovering of bound charges, finally we have seen that produced an electric field. So, this electric field will be now acting upon the minority carriers. So, drift current will be produced, and under steady state diffusion current is equal to drift current. So, net current will be 0 under open circuit. Now, this built-in potential for silicon and germanium are typically nearly 0.7 volt and 0.3 volt. So, this potential is such that, barrier potential is such that, if we consider from the P side, it will be rising and getting a maximum value. This built-in potential is VBI. Now, this built-in potential has an expression given by KT by E and natural logarithm of the product of Na Nd, which carry their usual meaning, that is the concentration of the acceptor atoms and concentration of the donor atoms, and divided by Ni square, intrinsic carrier concentration square. This term KT by E can be expressed as thermal voltage, that is called thermal voltage Vt, which is equal to K T, that is Kelvin temperature, divided by electronic charge, and K is Boltzmann constant. This constant is 1.38066 into 10 to the power minus 23 joule per Kelvin. T is absolute temperature in Kelvin, electronic charge 1.6 into 10 to the power minus 19 coulomb. So, now if we consider a room temperature, that is 300 degree Kelvin, which is generally done, all calculations are typically done at room temperature unless and until mentioned. So, Vt, if we calculate, this thermal voltage can be calculated using these constants. The electronic charge is 1.6 into 10 to the power minus 19, and this Boltzmann constant. So, it will be giving a voltage of 0.026 volt at room temperature. So, then we have the width of the depletion region, that is given by an expression under root 2 eta s divided by q into 1 by Na plus 1 by Nd into Vbi, that barrier potential or built-in potential has an effect on this depletion layer given by this expression, where this eta s is the electrical permittivity of silicon. If I consider this silicon material, it is 1.04 into 10 to the power minus 12 farad per centimeter. So, now if we know these two expressions, we can now find out what will be the typical value of this barrier potential or built-in potential and depletion layer width for a PN junction. Let us consider a silicon PN junction at room temperature 300 degree Kelvin, and it is doped with Na is equal to 10 to the power 16 per centimeter cube in the P region, and in the N region the doping concentration is 10 to the power 17 per centimeter cube, and intrinsic carrier concentration for silicon at room temperature is 1.5 into 10 to the power 10 per cm cube. This value we have been knowing already, we have done. So, now we can find out the built-in potential Vbi using these values. Now, this expression which we have with us is Vt, natural logarithm Na Nd by Ni square. So, for this particular typical example, if we substitute these values, we will be substituting thermal voltage with 0.026 volt and natural logarithm of Na, Nd and Ni being substituted for this example will give us a built-in potential around 0.757 volt. So, this is typically for silicon at room temperature, we will be getting a built-in potential around 0.7 volt. Similarly, if we want to find out the width of the depletion layer, we can calculate the width of the depletion layer for this example given by this expression, and here we will be substituting all those information given to us like eta s and q we know, these Na and D already we have with us, and VBI, that potential, barrier potential or built-in potential whichever we have found just now after calculation, that is 0.757 volt. So, this calculation of this expression under root will be giving us 0.329 micrometer is the width of the space charge region or depletion region for this particular typical silicon PN junction. So, typically you will be getting that at room temperature silicon has a barrier potential or built-in potential in the range of 0.6 to 0.8 volt, and the depletion region width is in the range of 0.1 micrometer to 1 micrometer. Because temperature plays a role, so you will be getting a different value for different temperature, but we are typically taking at room temperature at 300 degree Kelvin. Now, what will happen if we connect a voltage with polarity positive to the P and negative of the voltage to N? This particular biasing is known as forward bias condition. So, in forward biasing we connect P of the PN junction to positive of the voltage supply and N to the negative of the voltage supply. Now, here whenever you are applying a voltage as positive, we are connecting to the end of the P side. So, this positive terminal will be repelling these holes, similarly this negative terminal will be repelling the electrons in the N side. Now, these holes will be coming towards the junction and it will be neutralizing the atoms, there are acceptor ions on the P side will be neutralized, some of them will be neutralized. Similarly, these electrons will be neutralizing the donor atoms which are positively charged. That means, we will be now having a lesser depletion region, because depletion region contains all the immobile charges only, uncovered charges only. So, as the holes will be moving to the right, so the depletion region will get reduced, and if you consider from the point of view of the built-in potential, we are now applying a voltage with this polarity plus to this side and negative to this side, and our built-in potential has positive on this side N side. So, we have the built-in potential VBI reduced by this amount V. Our built-in potential is reduced. So, more and more holes will be easily crossing over to the N side, because it will be offered less potential barrier, because it has been reduced by this voltage. So, more and more holes will be crossing over to this N side, more and more electrons will be crossing over to the P side. That means, when we forward bias a PN junction, there is easier and flow of holes and electrons from P and N side, that is the diffusion current will be increasing, and with a very small change in the voltage being applied, we can have a very high exponential growth in the current in the forward biased condition. But if we consider now the reverse, that is, if we connect negative of the voltage to the P side and positive of the voltage to the N side, it is called reverse bias condition. What will happen is that now, as this negative terminal of the supply is connected to P type, these holes will be attracted by this negative polarity. So, they will be moving away from the junction. Similarly, these electrons will be attracted by this positive terminal of the battery. So, these electrons will be moving away from the junction. This is the junction. So, it will be going further away and away from the junction, and as a result of that, the more and more uncovering of the fixed or bound charges will take place, because these carriers will move away, they will be surfaced out. As a result of this, the depletion layer, depletion region will be now extending, it will be increased. And if we look from the barrier potential point of view or the built-in potential point of view, the built-in potential polarity is positive this side and negative this side, and we are now having this voltage applied with this polarity, negative to the P and positive to the N. So, now the barrier potential will be increased, this Bi was earlier and it will be now increased by this amount Bi plus B. That means, it will be offering very high resistance to flow of the charge carriers, that is, diffusion will be not taking place now. So, the diffusion current is 0. So, only current which will be flowing, but that is also in a micron order, is due to the minority carriers, because minority carriers are holes in the N type and electrons in the P type. So, the positive terminal of the battery will be repelling this minority carrier, which are holes from N side to crossover. Similarly, negative terminal will be repelling the electron to crossover. So, the current will flowing, a reverse saturation current it is called, will flow. IS is a reverse saturation current that will flow in this direction, which is opposite to the forward biased current. But this order is very small, as we know the minority carrier concentration is very less. So, this is very small and it is dependent on the mainly temperature. It will be increased if we raise the temperature, because you know that increase of temperature will be resulting in production of more and more minority carriers, more and more electrons will be breaking away from the covalent bonds of silicon or germanium, and more and more electron hole pairs are created when you increase the temperature. Other than that, the voltage, applied voltage does not have much effect on this reverse saturation current. So, this PN junction actually is the backbone of the semiconductor diode. Semiconductor diode is formed by bringing the P type and N type materials together. Whatever we have been discussing till now, PN junction, basically this PN junction forms the diode. This diode is formed by special processes, not just mechanically bringing this P and N together will not serve the purpose, because the crystalline structure will have to be maintained. It should not be disturbed, electrical characteristics should not be discharged, and that is possible only if we do the fabrication using standard techniques. And the processes which are used for this type of semiconductor diode formation are generally alloying, diffusion or ion implantation. So, the symbol for a semiconductor diode using PN junction is this one. So, this side is P and this side is N, this is the diode symbol. So, diode has immense application in electronics, starting from rectification. You want to produce a DC voltage from an AC voltage, we use semiconductor diode. Basic property which is exploited is rectification, and so many different devices use diode. We will be touching upon some of them. So, the p-n junction forward bias condition, this is the ID is the current flowing and Vd is the voltage across this p-n junction. In the forward bias, positive is connected to P and negative is connected to N, and the reverse bias has just opposite, positive is connected to N and negative is connected to P, and the current which flows in the reverse bias condition is reverse saturation current, that is denoted by Is. Now, what will be the relationship between the current and voltage in a semiconductor diode? That is an important relationship we must remember. This is given by ID equal to Is into exponential k times Vd divided by Tk minus 1. This expression gives the current flowing in a diode when the voltage across the diode or the bias voltage is Vd. K is a constant given by 11600 by eta. Now, eta is known as ideality factor of diode. The value of eta is 1 for germanium and 2 for silicon when the diode current is low, that is in the lower region of the diode current. These are different values, but when in higher level of diode current, you will be having same value as 1, eta value 1 for both germanium and silicon. So, the diode current ID is bearing a relationship given by this equation with the voltage Is, you know, it is the reverse saturation current which we have discussed, and the Kelvin temperature Tk is given by centigrade temperature plus 273 degree. This is Kelvin, mind it, it is not centigrade. So, this relationship actually is helpful in finding out the characteristic of the current versus voltage applied in a diode. So, now if we observe the volt ampere characteristic, Vi characteristic of diode, then this plot will show both under reverse bias as well as the forward bias the characteristic for two materials, germanium and silicon. This plot will be explaining. Now, under forward bias condition, here this portion, as you see, for typical values of threshold or offset or firing potential it is called, which is nothing but the built in potential or the potential barrier that we have discussed, which is typical values generally are taken as 0.7 volt for silicon and 0.3 volt for germanium. So, the voltage which is applied across this diode is Vd, that Vd must be greater than 0.3 for germanium and 0.7 for silicon in order that the current starts flowing in the diode. That means, when the voltage applied across the diode is less than 0.3 volt for germanium and 0.67 volt for silicon, there will be no current flow in the diode because the barrier potential is not overcome. So, after it is increased beyond 0.3 volt for germanium, you will find that the current rises almost exponentially. For a very small change in the applied voltage, you will be finding a huge change in the current, and this will be exponentially growing current. And similarly for silicon, similar curve, only that its barrier potential is 0.7 volt. Now, in the reverse bias condition, when you apply a negative voltage, that is reverse biased diode, you will find that current is very small, in the order of microampere, and even if you go on increasing the current, this current which is the reverse saturation current will not increase, it will be almost constant, because as I have mentioned earlier, it will be dependent on the temperature. Unless and until you increase the temperature, this current is not going to increase. So, it will be almost constant, but till what point you will find that if you go on increasing the reverse bias, a point will come when a very high voltage you apply, there will be sudden rise in the current, and that point is known as breakdown voltage, or it is also called a Zener voltage. That phenomenon happens, that breakdown of this diode will be happening because when you go on increasing the reverse bias potential, for a very high potential being applied, the electrons in the semiconductor will be getting a very high kinetic energy to break open from the covalent bonds, make themselves free, and this will be again knocking out other electrons, and this process will continue. It is like a chain type of process, and it continues. So, within a very short time you will be getting an avalanche of carriers being produced. So, suddenly there will be a very sharp rise of current because of this process, which is known as avalanche breakdown, because very high kinetic energy being gained by the electrons. They will be knocking out from the covalent bond. Similarly, the electrons which are knocked out, they will be also highly gaining energy, kinetic energy. So, they will be knocking out other covalent bond electrons. In this way, it will be a cumulative process. So, this avalanche breakdown takes place. So, suddenly current rises to a very high value. This is also known as Zener breakdown. Zener breakdown it is called because this phenomenon is actually exploited very or utilized effectively in Zener diode, which we will be discussing later. That is why from that Zener, this name also is known as Zener breakdown. And for Zener diode, basically this breakdown can occur at a smaller voltage, because Zener diodes is a special kind of diode that we will be discussing later. It is a very highly doped diode. So, when you dope it very highly, the breakdown voltage will be smaller. So, if it is lightly doped, this breakdown voltage will be, you will find that at a greater voltage this breakdown is happening. So, these two reasons, forward bias and reverse bias, are together described in this VI characteristic, which is a diagrammatic representation of that equation or representation or expression which we have got for diode current versus diode voltage. Now, because of this avalanche being taking place here, we must be very careful about at what voltage we are operating under the reverse bias condition, because this current is so high that the power will be very high, and the diode should be able to withstand this very high power. That power dissipation of the diode should be very, power dissipation capability of the diode should be very high. So, under normal diodes, if we apply and give a very high reverse bias potential, then it may not be possible for the diode to sustain that high power being dissipated. So, you generally do not apply a normal diode with such a high potential, and for that particularly Zener voltage, Zener diodes are used, which can withstand this high power. So, the power dissipation capability is more, and that is why the voltage, this maximum voltage beyond reaching the Zener breakdown is called peak inverse voltage, and that is a very important parameter for any diode, the maximum reverse bias potential that can be applied to the diode before entering the Zener region. So, PIV of a diode, that rating you have to always remember before applying it in the under the reverse bias condition. Now, we will be considering a diode, but before going to the practical diode, let us consider a theoretical ideal diode. Why I am calling it theoretical? Because practically you will never get a very ideal diode where you will be getting a characteristic VI characteristic like this. This is a purely theoretical diode, and why I am discussing, because before going to the actual practical diode, to analyze it, it is easier to take an example of a very simple diode which is ideal. Ideal in the sense that the ideal diode will not conduct, means whenever you apply reverse bias, the current is 0, totally 0. That is, it is like an open circuit. Under reverse bias condition, when Vd is less than 0, then it will be, current will be 0. So, this is like an open circuit, and whenever current is high, that the current is greater than 0, that means when current starts flowing, the voltage drop across the diode is 0, that is, it is like a short circuit condition. That means ideal diode has this type of characteristic that we can just assume that it is like a switch. It is under reverse bias, it is like an open switch, open circuit. So, it is opening, and under forward bias, when it conducts, it is like a short circuited switch because voltage drop is 0. So, the ideal diode is having this type of characteristic. When it is under reverse bias, current is 0, when it is conducting, the voltage is 0. So, this is just a theoretical diode which will be helping in further analysis, that is why we are bringing in this ideal diode. Now, this diode characteristic if I consider, then we can find out the resistance of the diode also. So, the resistance of the diode, basically when you have the diode characteristic is PDID characteristic, then if I want to find out the resistance of the diode, since it is a non-linear characteristic, you just mind it, it is not linear, the diode is not linear, only in the higher portion of the current region, this region we can assume to be almost linear, but it is practically it is not linear. If we want to find out the resistance of the diode, at the point where it is being operated, at the voltage which is being applied, suppose this voltage, and at that voltage this is the current. So, Q is the point where we are operating the diode, then the resistance which is known as DC resistance or static resistance is Vd by Id, that is this voltage by this current will give you the DC or static resistance. But if we apply a variable voltage like a sinusoidal voltage, then this resistance we will have to find out the dynamic resistance. Then how to find out the dynamic resistance? What you do is that you draw a tangent at that point where you are operating the diode, and at the tangent at the 2 points you just find out the difference in voltage and difference in current. That is, dynamic resistance will be given by del Vd by del Id, that is called dynamic resistance or AC resistance, because you are operating the diode suppose under a signal which will be bringing the current to this point and voltage to this point, as well as the other point is at this point, because it is a sinusoidal type of voltage or varying voltage, then we have to find the dynamic resistance of this diode. Now, another important factor for finding out the diode current is the temperature effect, because as we have mentioned, the temperature is affecting the minority carriers. That means reverse saturation current will be affected when you have a varying temperature. That means suppose we have now increased the temperature, what will be happening to this reverse saturation current? It will be increasing. Now, how much it increases? That is actually given by a law that for every 10 degree centigrade rise in temperature, the reverse saturation current approximately doubles. That means if suppose at temperature T1 we have a current IS1 reverse saturation current, and at temperature T2 IS2 the reverse saturation current will be equal to IS1 multiplied by 2 to the power T2 minus T1 by 10, because for every 10 degree centigrade it doubles. So, it will be power of 2 by that factor by which it is increased divided by 10. This will have to be counted when you have a variation in the temperature. Let us now find out the resistance of the diode. The diode resistance can be found out from the VI characteristic which we have just now seen, and from that VI characteristic, by finding out the ratio between the voltage and current at the particular operating point where you are operating the diode, it can be found out. So, let us find out the diode resistance. So, we have the characteristic VI characteristic of this diode as this type of characteristic curve, where it is the voltage across the diode and current through the diode. Now, as you can see that this is a non-linear characteristic. So, in order to find out the resistance, you have to do it at a particular point where you are operating the diode. Suppose I have voltage applied across the diode and the current through the diode given by a particular point Q, then you will be finding out the resistance which is known as static resistance, or it is also known as DC resistance, static resistance or DC resistance. So, static resistance is given by the ratio between the voltage and current at that particular point Q where you are operating. But when you have a signal being given to the diode like a sinusoidal voltage, suppose I am applying in the diode, then as you can see that this voltage signal, it is going from a very high peak value to a lesser value like that. Now, if we apply a varying signal, then AC signal, we have to find out the dynamic resistance. So, the dynamic resistance, in order to find out the dynamic resistance, you basically draw a tangent at this point where you are operating the diode and you want to find out the dynamic resistance, then at the tangent, 2 points on the tangent, you find out the incremental change of the current and change of voltage. So, this will be del Vd and del Id. So, the dynamic resistance is given by, or AC resistance is given by, or AC resistance, that is given by del Vd by del Id around this Q point, that is incremental change in voltage by incremental change in current. Now, let us do one example with all these expressions that we have studied till now, which is about a germanium diode. A germanium diode displays a forward voltage of 0.25 volt at 10 milliampere current at room temperature, which is 300 degree Kelvin. Standard room temperature is taken at 300 degree Kelvin. Now, find the reverse saturation current. For this example, you have to find the reverse saturation current. That means Is you have to find out, and here you have to assume that diode ideality factor eta is 1. This is given to you. Also, you have to calculate the bias voltage needed for diode current of 1 milliampere. For diode current of 1 milliampere, what will be the bias voltage to be applied when the current becomes, diode current is 1 milliampere and also 100 milliampere. So, these three cases, first of all it is given at 10 milliampere, then you have to find out for 1 milliampere and 100 milliampere at the same temperature. Temperature does not change at the same temperature. So, this is second part of the problem, and also you have to estimate the value of the reverse saturation current Is and also forward current 0.25 volt at 30 degree centigrade above room temperature. So, now the temperature is increased. At the new temperature, you have to find out the value of the reverse saturation current as well as the forward current. So, to do this example or solve this example, we will be taking that expression for diode current, which is ID equal to IS into exponential k Vd by Tk minus 1. This is the key equation which you have to use. Now, given in the first part of the problem is given that it is germanium and it is having a forward voltage of 0.25 volt. So, Vd is equal to 0.25 volt and the current which is flowing is ID is 10 milliampere. Bring it to the ampere scale, 10 into 10 to the power minus 3 ampere. I am bringing it to volt ampere scale, so that there is no mistake in between milliampere and volt scale to have a conformity. And temperature is mentioned as it is given in Kelvin. So, Tk is equal to 300 degree Kelvin, it is given. So, now in this equation, if you notice, we have to find out what? We have to find out this k. K is equal to 11600 by eta. Now, eta is given, ideality factor is given to be 1. So, it is simple, 11600 by 1 becomes 11600. So, k we have found out. Anything else? No. So, we can now proceed to find out the current. In the current expression, we can now replace 10 milliampere means 10 into 10 to the power minus 3 ampere is equal to Is into exponential to the power k is 11600 into 0.25 is the bias voltage divided by Tk, Kelvin temperature is 300 is given minus 1. So, this equation if we simplify 10 to the power minus 2 Is, you have to calculate this part, e to the power this whole term will be finally 1578.2.65 minus 1. So, now we can find out what is Is. So, Is will be equal to 6.34 into 10 to the power minus 7 amperes. So, this is the reverse saturation current flowing, or it is 0.634 microampere current is flowing. Now, next part of the problem is when 1 milliampere diode current is flowing. For 1 milliampere diode current, we have to now again write this equation, ID equal to Is into e to the power k Vd by Tk minus 1. This equation we are using again, but now what is given is that ID is given as 1 milliampere. So, 1 into 10 to the power minus 3, bringing it to ampere scale, and this current, reverse saturation current, is not changing because there is no change of current. So, that reverse saturation current which we have just now found out, that is equal to 6.34 into 10 to the power minus 7, that will be same, and exponential to the power 11600, that is also same, into voltage is now 0.25 volt Vd. No, the second part you have to find out bias voltage. Vd is not given. So, Vd you have to find out, and Tk is not changing, 300 minus 1. We have to find out that bias voltage what is applied. So, in this example we have now we have to simplify. So, simplification gives 1 into 10 to the power minus 3 equal to 6.34 into 10 to the power minus 7. This part you have to calculate. So, this will be, this whole part you have to now keep it as it is, that is 11600 V d by 300 minus 1. From here we have to find out V d. So, this calculation is giving the value of 38.67, this value is 38.67. So, e to the power 38.67 V d minus 1, this part we separate, equal to 1 into 10 to the power minus 3 by this whole term 6.34 into 10 to the power minus 7. So, now this V d we have to find out. So, you have to use natural logarithm for it. E to the power 38.67 d equal to 1 plus this right part will be, this part will be equal to e to the power 38.67 V d will be equal to 1 plus 0.1577 into 10 to the power 4. So, we can now find out right side, which is equal to 1578, that is e to the power 38.67 V d equal to this. So, now we can find out 38.67 V d equal to natural logarithm of 1578, and that is equal to 7.3639. So, now we can find out what is V d. So, applied voltage or bias voltage is, divide this by this, it will be equal to 0.19 volt. So, for this 1 milliampere diode current we have to apply 0.19 volt. Now, for the other part, that when the diode current is 100 milliampere, similar expression when I use I d equal to I s into e to the power k V d by T k minus 1, this expression again, just putting this value of I d here, which is 100 milliampere, then we get 100 into 10 to the power minus 3 ampere, same reverse saturation current 6.34 into 10 to the power minus 7, and e to the power 11600 V d we do not know, by 300 minus 1. So, that will be giving us, it will be equal to e to the power, again similarly proceeding, we will be getting e to the power 38.67 V d minus 1 equal to, the other side it will be equal to 100 into 10 to the power minus 3 by 6.34 into 10 to the power minus 7, and that will be equal to, this value comes out 15.77 into 10 to the power 4. So, therefore, this is equal to e to the power 38.67 V d minus 1 equal to this value. So, e to the power 38.67 V d equal to, we get 157701, and from here 38.67 V d you take out by taking natural logarithm 157701, that is equal to 11.97. So, V d, the bias voltage which has to be applied to get 100 milliampere current, becomes 11.97 divided by 38.67, comes out to be 0.3095 volt. So, this much of voltage is required. Now, you just notice that we are getting 0.3095 in this, for this 0.3095 voltage 100 milliampere, but earlier we have got for 1 milliampere we had to apply a voltage of 0.19 volt. So, even if we increase the voltage by less than twice, we are getting 100 times of diode current. So, for a small change of voltage, applied voltage, we are getting such a huge current change or rise, and that is very clear from that characteristic curve also. Now, third part of the problem, when temperature is raised, this is the third part, temperature is raised by 30 degree centigrade, from room temperature, that is temperature is raised by 30 degrees centigrade now. Earlier it was at room temperature, now it has been raised by 30 degrees centigrade. So, now what will happen is that the reverse saturation current will be now rising, and you know that for each 10 degrees centigrade rise, the reverse saturation current rises by 2 times. So, the new saturation current will become, earlier it was 6.34 into 10 to the power minus 7, that will be now increased by a factor 2 to the power 30 by 10 means 2 to the power 3 times, 8 times it will be increasing. So, this 8 times of this 6.34 into 10 to the power minus 7 becomes 50.72 into 10 to the power minus 7 ampere is the new reverse saturation current. So, when the saturation current is now, reverse saturation current is now increased, obviously the total current will also change. So, now the new temperature, Kelvin temperature is 330 degree Kelvin, because earlier it was 300, now it is changed by 30 degree. So, 330 degree Kelvin is the new temperature. So, total diode current for this new temperature will become, ID is now we have got it to be 50.72 into 10 to the power minus 7. So, 50.72 into 10 to the power minus 7 into exponential 11600 into 0.25, because voltage which is applied is 0.25 volt, it has been mentioned, and of course this Kelvin temperature is changing to 330 minus 1. So, this right side if you compute, it comes to 10 to the power minus 7 into this part is this part will be equal to 6553.31, this whole term becomes this. So, now computing this value we get 33238.4.1 into 10 to the power minus 7. To write in the microampere order, it will be now, or milliampere order, it will be now 33.24. It is equal to 33 point, because if you consider milliampere, 10 to the power minus 3 you keep, then 10 to the power minus 4 when you multiply 1, 2, that will be 33.24 milliampere is the answer. So, now you can see the change in the diode current when you raise the temperature by 30 degrees centigrade. Earlier it was, the diode current was, initially what was the diode current? It was 10 milliampere. Now, it has become 33.24 milliampere because of the change of the temperature, rise of the temperature. Because we have not changed the biasing voltage, only rising the temperature by 30 degrees centigrade has resulted in rise of the diode current to 33.24 milliampere from 10 milliampere. So, we have seen the effect of temperature change on the diode current.